Hello viewers, I hope this finds you well. And I remember a joke that I want to start with, that one of my teachers said some many years back, that physics is life. Physics is like oxygen that we breathe in day-to-day life. And I remember that teacher saying that if you don't like physics, if you don't love physics, irrespective of whether you are studying it or not, then you have no business of living. And that's how interesting physics is. And it's because of this that I feel motivated to always share something before the day ends, because I personally, I may say that I am deeply in love with physics. That's how interesting this thing is. And this is what has made me to at least make sure that every day or before the day ends, at least I share something on physics, the subject that I love most. I also love mathematics, which is my other second teaching subject. But for some of us who may be aware of this, you cannot even separate physics and mathematics. All of them, they are deeply intertwined, such that you cannot separate. In fact, I find myself sometimes asking whether the maths that I teach, whether it's maths or physics, so you can't separate them. Maths it's physics, physics it's maths. Yeah, they are so deeply intertwined, and you can't separate them. Now, in our today's lesson, I want us to learn a concept on magnetism. I want to believe every one of us have ever seen a magnet, and these materials that we are referring to as magnets find application in so many devices, in so many ways. For example, I know at home we have TVs, we have woofers, we have radios. If you happen to have maybe an unfunctional device, a device that is not in good condition, and you would like maybe to check what is inside, one of the things that you are going to find first are magnets, because without them, even the speakers, that given sound that you hear, it wouldn't be possible to have it. For example, the electricity, the power that we have, that makes us or that even makes our life more interesting. Without electricity, without the power, we would not even be having devices like TVs, because how could you be powering them? How could you be powering them? We have devices that have been meant, of course, to work specifically using alternating current. So the electricity itself is produced because of magnetism. Anyway, that's a topic of another day, but that's how interesting magnetism is. And I want us to learn something literal on something we refer to as magnetic domain theory. Magnetic domain theory. Magnetic domain theory will help us to understand why some materials are magnetic in nature, while other materials are non-magnetic in nature. What do I mean by magnetic materials and non-magnetic materials? What I mean is that those materials that get attracted by magnets are referred to as magnetic materials. For example, we have iron and its alloys, and we have those materials, for example, wood or even glass, that however much you try, they cannot be attracted by magnet. So what brings the difference? The magnetic domain theory is going to help us understand this better. And to start with, magnetic domain theory tells us that magnetic materials comprises of magnetic regions referred to as magnetic domains. Those small magnetic regions being contained in a magnetic material is what we are referring to as the domains. And it goes on to tell us that inside a magnetic domain, we have other subatomic magnets referred to as dipoles. So generally, magnetic domain theory tells us that magnetic materials contains small magnetic regions referred to as magnetic domains, and inside magnetic domains we find other subatomic magnets referred to as dipoles. I'll be explaining this using a diagram, but before I move to that, I always explain this concept to my learners by giving them a simple example. Take for instance a classroom. A classroom itself is made up of walls. We have the walls and the door. Now the classroom itself, I always take it as a magnetic material. And inside the class, we are going to find learners. And these learners have their desks and their chairs. So I always take my learners to be the domains. And the materials that they have, their belongings, I take them as magnetic dipoles, and this helps them understand what I mean by a domain and a magnetic dipole. And I want to clarify that, or to make you understand, by using the same elaboration. So we have a classroom. I take it as, or we take it as a magnetic material. Then we enter into the classroom and we find the learners. Now I take the learners to be the domains, and the learners have their desks, their chairs, their pens, and other belongings. So whatever now they have, I take them as the dipoles. And I believe that makes you understand what is magnetic domain theory. I want to draw a diagram here that is going to help us understand better what is this magnetic domain or a dipole. So I'm going to draw a material here. This material, I'm going to call it a magnetic material. It is magnetic in nature. Magnetic material. And this material is what I'm taking like a classroom. So inside this magnetic material, we have other materials or other groups, other regions. It is divided into regions. Now this region here is, we have one region, 2, 3, 4, 5. So these regions contains what we refer to as magnetic domain. So this one is a domain. And now inside that domain we have these other subatomic magnets that we are referring to as dipoles. So inside each domain we have a magnetic dipole. We have a magnetic dipole. If you look keenly on these given dipoles inside this magnetic domain, they are facing in different directions. Now, if a material is not magnetized, it looks like this. So to be more specific, I might say that this is a magnetic material that is not magnetized. If it is not magnetized, then the dipoles look like this. They face in different directions such that the resultant magnetic effect is equivalent to 0, or there is no magnetic influence at all, because in itself, though it is a magnetic material, it is not magnetized, and the magnets contained in various domains, they are facing in different directions such that their resultant magnetic effect or influence is equivalent to 0. Then I have another material that is not magnetic, non-magnetic material. So in a non-magnetic material, we have no domains nor dipoles. And if you are asked to give a simple difference between a magnetic material and a non-magnetic material in terms of magnetic domain theory, a simple explanation like this, that magnetic materials contains magnetic domains and magnetic dipoles is going to give the difference, because we have seen at all an unmagnetic material like glass or wood do not have these magnetic domains and magnetic dipoles. Then I want also to talk about something else here. How do we make a magnet then from these magnetic materials? Now, when materials that are magnetic in nature are subjected to an external magnetic field, these given dipoles that are facing in different directions are going to be forced by that external field to face in a certain direction, in a common direction. And when they face in a common direction, bearing in mind that this given dipole here has a north, and as a south, which of course generally makes a given domain to have dipoles facing in a given direction or in a common direction, and in a domain we have a north and a south. That means in a given domain we are going to find the north and the south, so that the general effects, or the general effects, or the magnetism in a given domain is going to have a north and a south. So a given domain will act as a magnet, because inside it has dipoles which have a north and south. And I believe you know that one of the properties of a magnet is that it must have a north pole and it must have a south pole. Now, when an external magnetic field is subjected or is taken near a magnetic material, we are going to have this scenario. So we have magnetic field, and we have a magnetic material, and in this given magnetic material we have said we have magnetic domains. Now, when this magnetic material is brought near a magnetic field, all the dipoles inside a given domain are going to face in a common direction and be parallel to each other. And when this happens, the resulting material is said to be magnetized. Magnetized material. Magnetized material. Now, in the process of magnetization, or in the process of realigning these magnetic dipoles such that they face in one common direction, there is something that occurs in these magnetic domains. The size of this magnetic domain, if subjected to an external magnetic field, can either increase in size or can shrink to become smaller. And when that happens, then reionization occurs, ensuring that all the dipoles have been directed or have been forced by this external field to face a common direction. And when that happens, then we say such material has been magnetized. So in a magnetic material, dipoles face in different directions such that the resultant magnetic influence or effect is equal to 0. But in a magnetized magnetic material, dipoles face in a common direction such that the resultant effect is of course will the effect will have the magnetic influence. That means the material will be having those given properties of a magnet, will be having a north and will be having a south. The material itself, once magnetized, will behave like a magnet. And I want to mention something here. Sometimes if the field is not strong enough, not all dipoles are going to be aligned such that they are parallel to each other and they are going to face a common direction. Now, if that happens, we say the material is magnetized but not completely magnetized. But if the dipoles are parallel to each other and facing a common direction, then we say such material has reached magnetic saturation, or the material is magnetically saturated. And when a material is magnetically saturated, it doesn't matter the force of the magnetic field that material is subjected to. It can no longer be magnetized further. It cannot be magnetized further. And if you continue subjecting such a material to an external magnetic field, what is going to happen is that the material will start losing magnetism. The dipoles inside those given magnetic domains are going to lose or are going to gain more kinetic energy, and now they will disorient themselves. They will start facing in different directions because of the increased kinetic energy they get from the external magnetic field. So when a material has reached magnetic saturation, you are not supposed to subject it to any more magnetic field, because instead of making it more magnetic, then it will that material will start losing magnetism. And finally, I want to talk about two different types of materials still connected with this given magnetic domain theory. We have those materials whose magnetic dipoles inside magnetic domains are going to be easily aligned to face one common direction. But if the external field is removed, those materials will or the orientation of those given dipoles is going to change. They are going to revert back to their original arrangement, and such materials, we refer to them as soft magnetic materials. They are easier to magnetize. It is easier to align their magnetic dipoles in one common direction, but if you remove the magnetizing field, then the orientation reverts back to the original. There are other materials that are difficult to align their dipoles to face in one common direction. And if those materials, or if you manage using an external field to align magnetic dipoles in one common direction, then those given materials are going to retain their new orientation. And those materials that are easier, that are hard to change or to align dipoles to face one common direction, but if you manage to align them in one common direction, they are going to retain their new orientation. We refer to them as hard magnetic materials. In other words, we say that hard magnetic materials are difficult to magnetize, but once magnetized, they are going to retain magnetism for a longer period of time. But for those soft magnetic materials that are easier to magnetize, they are going to lose magnetism easily, or their magnetism is not going to stay for a longer period of time, especially when the magnetizing field is removed. I want to believe you have learned and you have enjoyed the lesson. I want to end here, and kindly remember to subscribe, share, keep tuned, and we are going to interact in the next clips. Enjoy yourself and stay safe.